All right, so this is going to be another video about representing functions as a power series, and this one's a little bit tricky, that's why I'm making a video for it. But as this function, the f of x is equal to ln of 1 minus x squared, and it's centered at x equals 0. Okay, the first thing I'm going to be doing is trying to figure out how to get it somehow to be in a form that's similar to this, where that's a over 1 minus r. Just because that's our geometric series, we're going to use that for our power series. So the first thing I'm going to do is rewrite f of x in the following way. So you basically have ln of x plus 1 times x minus 1 because I just factored out that 1 minus x squared. Now from here, I'm going to use my log rules to break up that logarithm to be ln of 1 plus x plus the ln of 1 minus x. Okay, again, the whole goal is to figure out how to get it to look like this. And hopefully you see that if you take the derivative of this, of f, you end up with something that looks like this right here. So you're going to end up with 1 over 1 plus x minus 1 over 1 minus x. Now this plus became a minus because you end up multiplying by the -1 inner derivative here. So if you do the derivative of that with chain rule and you multiply by -1 at the end, it's the same thing as putting a minus there. So that's essentially why I did that. We're going to use that geometric series to figure out the power series for that. So I'm going to rewrite both of these terms, this one and this one, to match what I have over here. It's going to look like the following. We're going to have 1 over 1 minus -x minus 1 over 1 minus x. This one's already in the format that we have here, so the second one's kind of easier. The other one just has a negative, basically, so we can figure out our r. Okay, your r for each one of these, first one's going to be -x, and the r for the other one is just going to be x. So those are your two r's for that derivative. Again, we still have to do the integral at the end to figure out what that original function is, because right now we're only working on the derivative and we need the actual, original by the end. All right, so first thing I'm going to do is this first part, I'm going to make that as a power series. So the derivative is going to be equal to summation from n equals 0 to infinity. And I'm going to factor out that -1, and it's going to be times x to the n. And then I'm going to be adding the x to the n from the other one. I'm going to put brackets around this whole thing just so it's easier to see. Okay, so the first one, this one is this one right here, and that second one, this one right here, is this one right here. So kind of broke it down like that. And that's just a derivative. Again, we haven't actually found the power series for the original f of x. This is just a derivative for now. So what we're going to do for the derivative is I'm going to factor out, I noticed that there's an x plus n for each of these. So I'm going to factor out an x to the n. So you're going to end up with something that looks like this. And that should have been a minus. My fault. Okay. So that should have been a minus. Okay, that's just this copy error there. And this should be -1 here, and you end up with something like this. Okay, now what's great about this is that it's a really easy antiderivative. So now when we're going from f prime to f, so now we're going to f of x, we can just use reverse power rule here. And the x to the n just ends up being x to the n plus 1 over n plus 1. And this second part right here is basically a constant. It's not really going to change. So we just have -1 to the n minus 1. You don't really have to worry about that. Now, the reason this works is because you're actually doing the antiderivative with respect to x, and there is no x in that second part. There is an x with this x to the n, so that's why I had to do reverse power rule on that.
All right, this is going to be a really quick note. I did not actually include a plus c when I found this antiderivative. Now, technically you're supposed to, but the reason I didn't is because in this case, c is equal to 0. And the reason for that is f of 0 is equal to 0. If you plug 0 into the original function, that ln of 1 minus x squared, it's going to be ln of 1. ln of 1 is equal to 0. And if you put 0 in for x with that power series, you're going to end up with 0 plus c. So c ends up being 0 here, so I actually did not write it in, but it is still good to check that to make sure that you take that plus c into account.
Okay, now this looks kind of messy. This does work as the answer, but you can actually make this look a little bit better. Before I do that, it's probably smarter to do the interval of convergence, and I can base the interval of convergence based on this derivative here. It would be between -1 and 1 for this f prime. So that means it's also the interval of convergence for f of x. So I'm just going to highlight that there as the interval of convergence. And this other one, I'm going to write it a little bit simpler. Now, again, you don't have to do this, but sometimes you'll see teachers prefer you to do it this way. So I'm just going to show you really quick. It's not that complicated. But basically what I'm going to do with this orange is I'm going to start writing out the first, 4 terms until I get a pattern. And then I'm going to rewrite it based on that pattern. So let's just say n is equal to 0 for the first one. N is equal to 0. So if n is equal to 0, that first term is just going to be x to the 0 plus 1. So it's just going to be x to the first power divided by 1 times, and then it's going to be -1 to the 0 power minus 1. So it's just going to be 0. So that first term is just going to be 0 if n equals 0. Okay, so if you plug in n equals 1, you're going to end up with x squared over 2 times -1 to the first is -1. -1 minus -1 is going to be -2. So I'm just going to put -2 in like that. Okay, and then I'm going to do the next one for n equals 2. You should see this pattern pretty soon. You're going to end up with x to the 3rd power over 3. So if you put a 2 in for this n right here, it's going to be -1 squared, which is 1. 1 minus 1 is 0. So you're just multiplying this by 0 here. And as you can see, just like the n equals 0, the n equals 2 also ends up with 0 for the answer. So this one ends up just canceling out like that. Okay, the next one, n equals 3. It's going to be x to the 4th over 4 times. Now it's going to be, again, that -1 minus 1, because if you plug in for this n right here, 3, it's going to be -1 minus 1, which is just -2. So I'm going to put a -2 in there. Okay, again, you can kind of see the pattern already, but let's just do one more for fun. N equals 4. It's going to be x to the 5th over 5 times 0, once again. So you end up canceling basically the 0, 2, and 4 term for this. And it would be even after that. The n equals 6 would also cancel out. So now what we can do is rewrite what we have here into our own series. So that's what I'm going to do. I should probably put a plus ... here. Okay. All right. So what I'm going to do here is make a completely new series based on, I'm basically rewriting all these n's to ignore the 0. So this n equals 1 right here, this is going to be our n equals 0. This is not going to be used because it's a 0 term. This one's going to be our new n equals 1, and so on, because the rest of them are zeros. Okay. So this is going to look a little bit neater. You don't have to do this again. Sometimes it's expected of you in your class though. So it's going to be the sum from n equals 0 to infinity. And it's going to be, if you notice, if with the new n equals 0, the power becomes a 2 here, and then when it's a 1, it becomes a 4. So if you notice, the change is 2 each time. So I'm just going to do x to the 2n, because whatever that power is, whatever that n is, the power ends up being a difference of 2 each time it changes. So every time n goes up by 1, the power up there goes up by 2. So it's going to be 2n. Now, in order for the first one to work, since n is equal to 0 and it has to be a 2, you have to have a plus 2 up here. So it's going to be x to the 2n plus 2. Now, the powers match on the bottom, so I can just divide this by 2n plus 2. So you end up with something like that. X to the 2n plus 2 over 2n plus 2. And then it's multiplied by this -2. If you notice, there's a -2 here, there's a -2 here, there's going to be -2 everywhere else as well. So you can just multiply it by -2, and then you end up with a little bit of a simpler answer than what we got with the orange. But again, the orange answer works just as well as the blue. It really depends on what your teacher is looking for. But you end up with a series for f of x that's represented by that on the interval of convergence of -1 to 1. So that's another representing functions as a power series. If you have any questions about anything in this video, let me know.